And I'll share my screen. I think you guys see my screen now, right?
Yes, we do.
Awesome, awesome, very good, very good. I mean, I know that it's 8 a.m., so it's not the best time, and 8 a.m. with Zoom, so it makes you even more sleepy. But I taught this course like a few years ago at 8 a.m. and it, actually, surprisingly, it wasn't that bad. So, all right, let's start. Jeez. This is 175. Dynamics of aerospace vehicles. Is for short, I mean, I just call it flight dynamics. So we'll start with what is flight dynamics? So flight dynamics, and wavy definition for it. It's simply, so this is our MAE 175 course. It's actually the intersection of two courses or two disciplines. It's aerodynamics, which is 136. This is why I'm saying, okay, we're gonna use some material from there. No worries at all if you have not taken the course. But if you did, you'll feel more comfortable in the first few lectures at least, or maybe the first lecture only. And this is plus dynamics. Okay. Please, if you have any question, no matter how you feel it's a naive question, it's never naive. Please stop me and ask. I mean, this is why we're doing the lecture, right? Actually, it's not that, I mean, because this is recorded already. I mean, you can just go and watch it and, you know, we're fine. So actually the main points that we have some interaction. I know that Zoom precludes good interaction or doesn't probably allow good interaction, but let's try to make the, you know, the best out of it. So if you have any questions, stop me. Flight dynamics, this course that we're about to study is the intersection of two disciplines, aerodynamics and dynamics. And let's try to refresh our memory about what is aerodynamics and what is dynamics. So let's recall what is a typical problem of aerodynamics. Like here is, let's keep the color code here. So for example, here is a typical problem in aerodynamics. Given a wing shape, what we call airfoil, right? And this is moving with some speed, V. So it's making some angle with its own, the body is making an angle with the speed vector, this angle, we call it alpha, the angle of attack. And when we have a wing moving in the surrounding air with a speed and some non-zero angle, we actually got two things. We get lift force that is normal to the speed, and we get some opposing drag force that is, like I said, it's opposing to the velocity. So this is a typical picture in every single aerodynamics book. And a typical problem is what is given and what is required. Like if I have a block here, if I have a block and I call it, hey folks, this is an aerodynamics block, what is typically given as input? Like in any homework problem in aerodynamics is, okay, here are the givens and please compute blah blah. What is given in your opinion? Any suggestions, even if you have not taken aerodynamics? Let's, given this picture, what do you think? What should be given from an engineering point of view? What should be required?
Maybe the fluid velocity.
Yeah, great. Exactly. So I have an airplane, so I know how fast I'm flying. I'm driving my car and I know how fast I'm driving my car. And probably I know that the geometry, I know the angle of attack, I know the geometry of my wing, you know. And then, okay, so I'm given all this. What is required? Any suggestions?
You want to find maybe the lift and drag and maybe the pressure coefficients.
Exactly. This is a typical problem in aerodynamics. Find the aerodynamic loads, the forces, which is here, I mean, maybe lift, drag, pitching moment, pressure distribution. So the forces or the loads, right? So this is a typical problem in aerodynamics, all right? So when you study an aerodynamics course, you should be able to answer this question with a reasonable accuracy. This is, if you don't like this type of problems, so don't go and study aerodynamics. So what about dynamics? I mean, you have all taken dynamics, so you can keep silent. Okay. So in a typical dynamics problem, what is given and what is required? Find what? What is typically given in a dynamics problem? So maybe a ball is, or a bead is rolling or sliding over a surface. Given blah blah, find blah blah. What is that? Given what? What are you given? Maybe the forces.
Given like initial forces, geometry.
Exactly. We're always given the initial conditions, initial velocity. That's right. That's exactly right. Initial condition, initial velocity. But in addition, in order to move forward from this initial position, they are not sufficient. I also need the applied forces, right? So the applied forces are applied loads, and then, okay, so here are the applied forces, and here the initial condition. Find what? Maybe find the ensuing motion, velocity as a function of time, displacement as a function of time, velocity as a function of displacement, whatever. It's some measure of the ensuing motion. Given forces, applied loads, applied forces, find the ensuing motion under these forces. And please, if you have any question, stop me. So these are the two like isolated blocks of aerodynamics and dynamics, and the role of this course is to combine them. The airplane is a body or a particle that experiences motion under the action of some forces. These forces are actually coming from the surrounding air. So the loads, the aerodynamic loads coming from the air, these are the forces acting on the body, and this motion will actually affect the velocity of the airplane and the angle of attack and so on and so on. So this combined block, which actually seems to assume a feedback loop kind of thing, naturally without we design a controller, this is actually the flight dynamics. Any question about that? In fact, we can do three types of studies, I mean, several types of studies, but there are three common types of studies regarding this interaction between aerodynamics and dynamics. There is one type called, let me use different colors, maybe performance. There is flight dynamics, like I said. And there is something called, the name is expressive, dynamics of flexible airplanes. So let's see. This is actually, they are related to courses. This is MAE 158, which aeronautical engineers, the aerospace majors, they are currently taking it. This is our course, like I said, the 175. Here, there are no courses, actually. This is quite an advanced topic. So you can find it in research papers and stuff. There is no even course in grad school. So, okay, what do we mean by each branch of them? So here we treat the airplane as a point mass. So the typical picture that you find in every airplane performance book is Here is a point mass representing the entire airplane. It's moving in this direction with a velocity v, making an angle gamma or theta with the horizon. So if gamma is positive, it's climbing. If gamma is negative, it's descending. If gamma is zero, it's cruising, and so and so. And of course, there is a, a thrust force that is propelling the airplane forward. It's in typically in the direction of the velocity. And like I said, once we have a velocity, any object, no matter how ugly is that object, it will experience some upward lift, normal to the speed, some opposing drag. The fact that the shape is nice makes the lift bigger and makes the drag smaller, but any object will experience upward lift and opposing drag. And of course, the inevitable force, which is the weight. So this is really the typical picture in every airplane performance book. And we study this point mass, the motion of this point mass under the action of these forces, and so on, and some basic aerodynamics for lift and drag. So there is this combination of aerodynamics and dynamics on that level, assuming that the airplane is a point mass. This is what is all the 158 course is about. How many degrees of freedom, when you see this picture, how many degrees of freedom do we have for a point mass in the space? Any suggestions?
2.
Yes, it's 2 in the plane, right? Yes, it's a, I'm sorry, my drawing is planar. So yes, it's one translation X, one translation Y, but if I'm in 3D space, there'll be 3, right? So this is 3 degrees of freedom along X, Y, and Z simply. 3 translational degrees of freedom for a point mass, correct? And okay, so how this is different from flight dynamics? So this is not our concern. Actually, in flight dynamics, we do a little bit more advanced in the sense that we treat the airplane as a rigid body. It's not a point mass. So what do you mean by that? I have, if it's a body, I have to, sketch the geometry of the body. And this is the velocity vector. It's still making some angle with the horizon. This is gamma, but it's also making some angle with, oops. All right. It's also making some angle with the axis of the body. Can you suggest a name for this angle between what? Between the body, the black axis, and the velocity of the body, the green velocity vector. Any suggestion for this angle? Velocity between the body, I'm sorry, angle between the body and the velocity vector.
Maybe beta?
Close enough. Well, it's actually here, right? Angle between the body, the wing or whatever, and the velocity vector. This is really the angle of attack. So this is alpha, right? The beta is another angle of attack, but it's a little bit more advanced. So we're going to talk about it later. So it's this, the simple notion of the angle of attack is alpha. Here is alpha. All right. It's simply the angle between the body, some reference direction in the body, and the velocity vector. All right. So in the point mass model, we always assume that the body is aligned with the velocity vector. The body cannot rotate with respect to velocity vector. So here we don't have this assumption. So we have additional degrees of freedom. The body can translate, of course, along X, Y, and Z, fine, like here. But in addition, it can also rotate. Okay. So how many degrees of freedom do we have here?
Would it be 4?
Okay, that's I mean it's correct to a big extent because it's the 3. I'm gonna add 1 rotational degree of freedom, but what about, let's generalize it to the max? Well, I can rotate about this
6.
axis. Exactly, I can rotate about this axis, and that axis, the 3 axes. So in the very general case, they will be 6 degrees of freedom, 3 translational degrees of freedom, and 3 rotational degrees of freedom, simply, right? So this is actually the topic of our course here, but to complete the story, we can do the following. So I can assume, or I can relax this assumption of the rigid body. Like I can relax this assumption of the rigidity of the body. I can assume that the body is flexible. So what do we mean by that? So if you simply have, here is a fuselage, here is a vertical tail, a funny thing, and here is the wing. Where is the? You guys still see? I'm still sharing my screen, right?
Yeah.
Okay, very good. So this is the wing, and remember the wing, there is every section, like this section, for example. What is this section? This is simply an airfoil, right? So it has some upward lift and opposing drag. So I have a little bit lift coming from here, a little bit lift coming from here. So every section is providing some lift. So on the wing, I have lift distribution, and the wing is just clamped here. So it looks like a cantilever beam. Recall 150, the course 150, solid mechanics. So it looks like a cantilever beam subject to some distributed load. What will happen? Well, will flex a little bit upward in the direction of the load, correct? So now each point has a degree of freedom. This point moves that much, this point moves that much. So each point has a degree of freedom in addition to the six. The six are for the entire body, but within the body, each point has its own degree of freedom, or even set of degrees of freedom, few degrees of freedom for each point. So how many degrees of freedom total do we have?
Infinitely many.
Exactly. We have infinitely many. So I would naively here say 6 plus infinite. All right. So, I mean, in reality, we always have to truncate. We discretize. Let's say we're going to take 100 points along the left wing, 100 points along the right wing. I mean, another 100 points along the length of the body, another, 50 points in the horizontal tail, and so on. So we will have many degrees of freedom. They will not, so practically speaking, they will not be infinite. We're going to truncate and discretize as we always do, but intrinsically they are infinitely many. So this is typically the taxonomy of taxonomy of the studies that combine aerodynamics with dynamics. I can do it on several different levels. In this course, we will do it on that level, assuming rigid body, so the body will rotate whenever you command. And this is actually very interesting. This picture, I'm sorry if it's that messy. We can zoom here. This picture says a lot, actually. What do we mean? When the pilot pulls the stick, so tries to command the airplane to climb, all right? The pilot, what he or she actually has at his or her disposal for control is to rotate the body, okay? Rotate that black axis of the body. It's as if you're holding the body and you're rotating it. Well, you have no control over rotating the velocity vector. So this is actually an issue, and this is the main difference between the performance and rigid body, is that whenever you command the climb or something, well, for the climb, I want the velocity vector to go from horizontal to upward, like in this picture. Well, this may not happen. What may actually happen is that the body rotates, and indeed, this is what happens. So the body rotates, but eventually, and we will learn this through the course, eventually the velocity vector will follow the body, will follow the axis. We'll see how this happens. But I hope you get the difference here. Here we don't account for the body rotation whatsoever. It's always assumed to be aligned with the velocity vector. I mean, it's good for first computations, preliminary results. But if I want to go more detailed, I mean, of course, the body rotates. And if I want to go more and more detailed in real research or real airplane design, build, fly kind of activities, I'm not saying about the design, build, fly competition. I'm saying in the, and for an airplane manufacturer like Boeing and Lockheed Martin, every airplane manufacturer has their own dynamics of flexible airplane code kind of thing. All right, if you have any questions, stop me, please. So let's see. Today I will review some concepts from aerodynamics, because I know that 136 is not a prerequisite for this class, although we really need some materials from there, because the study that we're doing is inevitably relying on some aerodynamics material. I mean, flight dynamics on its own is just an intersection of aerodynamics plus dynamics. I mean, dynamics is nothing but force equal mass times acceleration, simply. Dynamics is so simple. But I mean, we need some review of aerodynamics. What does nature give us when we fly an airplane? When we push or pull an airplane or any object through the air, what does nature give us? So we will do some review of basic aerodynamics, and usually here is how it goes. Usually we go from 2D. So I'm gonna have here review. So the rest of the lecture today is we're gonna do a review of some basic aerodynamics. Like these are the take-home messages that you got out of the entire course of 136. You can say it's a summary of 136. So if you have taken a 136, things should be familiar. If not, you will be hearing it for the first time, which is not too bad. So typically we go from the basic element, the airfoil section. So this is 2D airfoil. Then once we know how to treat 2D shapes like airfoil, we go 3 dimensions. So we go like maybe 3-dimension shapes, so the 3D wings. Because here, any section here is this airfoil, right? And once we figure out the aerodynamics of our wing, we go to the next level, which is, of course, the entire airplane. So this is the evolution. Today we will review 2D airfoils and 3D wings, which you should have seen in 136, and the aerodynamics of the entire airplane. This is what we will be taken in either 158 or 175 on different levels, as we discussed. So let's do now the 2D aerodynamics. Any questions? All right. I have an airfoil. The airfoil is moving, say, horizontally. I can always, we always do this trick, which is due to Leonardo da Vinci in the 16th century. Is we can always stop the airplane and assume that the air coming in the opposite direction. We can always do that as long as the motion is steady. Like if it's an unsteady maneuver, this assumption is wrong. I mean, for some reasons that we can discuss later if you're interested. But if the wing is moving at a steady speed, everything is nice, constant angles, then yes, strictly speaking and mathematically speaking, you can really, this situation is equivalent to the situation of a stationary wing and the wind coming. What is happening? Let's see. Okay, the wind is coming from the opposite direction. This is velocity v. Obviously, we have some angle of attack alpha. This is the chord length c, and the black line is the chord line that connects the trailing edge and the leading edge. So this chord line is making an angle alpha with the velocity. And like I said, I'm given the geometry, I'm given the velocity, I'm given alpha, and I'm required to determine the aerodynamic loads. So actually, any shape like an airfoil or anything, when it moves through the air, so it experiences some lift and some opposing drag. And let me, every year I forget this. So in the 2-dimension, I just give them little l and little d. So, okay, I mean, we need to compute these little l and little d. Here are the relations. They're so simple. 1/2 rho v squared. So rho is the density of the air. V is the speed that you give me. And these loads are actually proportional to the chord length. And so this is just a non-dimensionalization. There is a coefficient of lift, and the same for drag. So okay, fine. I have everything except the lift and drag coefficient. So how can I determine them, please, in order to compute my L and D? These are the target to get the loads. Well, the lift coefficient is. It has an interesting story. It actually depends on the angle of attack. And it moves linearly with the angle of attack. You increase alpha, the lift increases linearly, everything is fine until some limit. And this limit is what we call stall. So here, this is what we call stall. And we don't fly there. No civil airplane flies there, or even, I mean, some military do, but it's even military. They are not all military airplanes fly there. It's very critical regime. It's not only about you're losing lift, you're actually losing control of the airplane. We're gonna have some discussions about this every now and then, but it's not the main topic of our course. It's actually not well understood in the community anyway. High nonlinearities, high unsteadiness, even if you fly at fixed speed and fixed angle of attack. Lots of vortices going back and forth. It's quite complicated flow field anyway. Okay, we fly here in the small angle of attack regime. Everything is nice. The lift varies linearly with the angle of attack. So it's like a linear relation, A plus BX, where my X is the angle of attack alpha. So the A, we call it CL naught. So this distance, this distance, we call it CL naught. Like this. This is CL naught. And B times X, so something times X, my X is alpha, so something times alpha. This something, which is the slope, we call it CL alpha. So in conclusion, CL is a constant, CL naught, plus CL alpha times alpha. All right. CL alpha is the slope, and the slope is simply 2 pi for flat plate. Every airfoil shape, every shape has its own slope. So some shapes have higher slopes, so they have higher capability of generating lift. Of course, if they are nicely designed. The airfoil is one of the best shapes. So, but anyway, so if not given in that course, you're free and you're allowed to take CL alpha, the slope as 2 pi, all right? CL alpha of the 2-dimensional airfoil. Okay, what about the drag? Well, the drag is actually in this 2-dimensional airfoil on that regime, in the small angle of attack regime, is fairly constant. You can assume that it's actually a constant because it's really due to friction only. So to first order, it's just the friction drag, which is a constant. It's just function of the geometry. Give me your geometry, I tell you how much friction you get, and that's it. So every airfoil comes with its own CD coefficient, small angle of attack. Of course, in the stall, the drag increases dramatically, and we don't fly there anyway. So lift to drag aerodynamic loads are actually varying proportionally, quadratically with the speed. And like I always do, you can test this hypothesis easily. You drive your car, get your arm outside on the highway, and you will immediately feel that your arm is pushed upward and backward. Lift and drag, you will feel this really, and you can always feel the quadratic relation, because you can, if you increase your speed, if you push your gas pedal a little bit, you will feel a significant increase on the force on your arm, because it's a quadratic. If the velocity is doubled, the forces will be, you know, quadrupled. They will be multiplied by 4. So so that you can easy test. For lift and drag, they depend on the shape. Your arm is not nicely a wing, like an airplane wing, so you will not feel these details. But for an airplane wing is actually a constant plus constant times alpha. This constant is close to 2 pi. It's exactly 2 pi for a flat plate. The drag is fairly constant for a small angle of attack. Any question about that? Any question? So what about CL note? Well, for CL note, actually, you have two common types of airfoils, what we call symmetric airfoil. So the chord line, or the line, the curve that connects. So the chord line is always the line that connects the two edges, all right? Now it coincides with a curve that separates the upper half of the thickness of the airfoil and the lower half. So so the airfoil is symmetric around its chord line. In this case, we don't have CL note actually. We don't get lift at a 0 angle of attack, because the CL note is the amount of lift that you get at a 0 angle of attack. For other airfoils, camber, what we call cambered airfoils. So this is gonna be, here's the chord line, here is the curve that separates the upper half and lower half. So we're gonna distribute the airfoil around. All right. Here, the chord line is always here, right? This is the chord line. Just connects directly the leading edge and trailing edge. Well, this is different from the black curve now. So anyway, this is what we called cambered airfoils. For camber airfoil, they have non-zero CL notes, and it really depends on that camber. So the maximum camber is we call it H. So the CL note is really proportional to this H. It's 4 pi H over C if it's a circular arc camber. Any questions? All right. So when I have an airfoil like this, yeah. In fact, there is a pressure distribution. So there are like forces everywhere acting on every piece of the airfoil, and we just simply integrate over the airfoil. Like we sum all these forces and to get the resultant. And the resultant is really the lift force and opposing drag, right? When we sum all these little forces to get a single force that has two components, the single force acting on one point, this point is called CP, the center of pressure. The name is expressive. If you sum all these pressure distribution, And to get a one force, a single force, a resultant force, it will act at that center of pressure. Obviously, there is no moment. There is no moment at this. I mean, a moment, I mean a load, a torque. So you sum all these forces, you get just a single force. Now I can transfer this force to any other point. It will transfer by a force and moment, right? And let's see. If I have my chord line like this, this is leading edge, this is quarter chord, this is half chord, 3/4 chord, and trailing edge, and so on. And I'm looking for a reference point. We have seen, or we stated that the lift has two main contributions. It's one due to camber, CL note, and one due to angle of attack. And by the way, it's an interesting thing here, because when we write the lift in this expression, it immediately gives you maybe the origin of the lift, or how we get lift from objects physically. It's actually due to curvature. Why? Because here's a flat plate, and here is the flow over a flat plate. It doesn't curve at all, so I don't get any lift. I don't get any force out of this guy. All right. So, but once I have my flat plate as like this, so the flow now will go along a curved path. All right. So I forced the flow to go along a curved path by having an angle of attack, because the flow will have to move around the body. So if it goes along a curved path, I will get a lift proportional to that curvature actually. And I can do the curved path by one of two things. I can deflect my entire body, so the flow will deflect accordingly, or my body is naturally curved, like in the cambered airfoil. So the flow comes horizontally, will have to move around the body, but the body is curved. So I will get a lift due to this curvature. So hence the lift is due to camber, so curvature of the body itself, which makes the flow go around a curved path, or the lift due to angle of attack. So I deflected my body to create a curvature of the flow field. Any question about that? These two components act, one of them, CL note, act here. And this is the lift due to camber. CL alpha alpha act here. Let's have different color. Maybe the other way around. Because this was blue, here is the CL note. This was maybe a greenish thing, CL alpha alpha. So when I sum all these pressures, I get two main components. One that is independent of the angle of attack, and one that is varies linearly with the angle of attack. Why are we obsessed with the angle of attack? Because the airplane changes its angle of attack throughout the flight. So I want to always study things, how things change with the angle of attack. If they're plane, it maintain good characteristics at a wide range of angles of attack, or at least the flyable range of the angle of attack. So okay, here are the two main lift forces. Where is the resultant? Is it at the leading edge, at one of these 2 points, in between, or where is the resultant of these two forces? Any suggestions?
The single resultant should be between those two, right?
Exactly. So this is the resultant. which is the total lift coefficient. I mean, if they are exactly equal, it will be exactly in the middle. In general, it will be shifted a little bit toward the larger of the two. Okay, so this is the center of pressure, right? The point at which the resultant acts. At this point, there is no moment, there's no torque. And what do you think? So if at zero angle of attack, if alpha is 0, so this green component vanishes. I only have the blue. The center of pressure will be where?
At the half chord.
Very good, at the half chord. And as the angle of attack increases from 0, so this component will have some non-zero contribution. The center of pressure will move from half chord forward or backward.
Forward.
Forward, very good. So the CP moves forward as alpha increases. Okay, so it's not a constant point, it's not fixed point. It doesn't it's not a good candidate to serve as a reference point. It actually changes throughout the flight, because like I said, we change the angle of attack throughout flight. I'm looking for a good candidate for a reference point. So let's look for a good candidate together for a reference point. Well, we can take the leading edge, the quarter chord, like I said, half chord, 3/4 chord, trailing edge, but it should have a significance. Do you guys have any suggestion? Anyone has a, I know it's not obvious, so we're trying to thinking together. Any suggestion?
Would it be the quarter chord?
Yes, any reason behind, any justification? I mean, again, just thinking together.
Maybe because the center of pressure slowly approaches the quarter chord, and that's where it will, I guess, be the end.
I see. So that's actually it's a good suggestion. Let's try to study it in more details. Let's take another point. Let's take half. Here is, so I'm gonna take the half chord as my reference. So I have here the chat. Yes, exactly, because this is why what they said in 136. So let's see the reason. I mean, like a reasonable justification for it. Well, I have two contributions, right? CL note in blue and CL alpha alpha in green, and I can transfer both to any point I like. And when I transfer a force, it goes by a force and moment, as you guys know. So let's transfer everything to the half chord. Well, CL note is already at the half chord. When I transfer the CL alpha alpha to that point, it will add to the CL note. So I will have my resultant here at the half chord. This is the CL, but I will have a pitching moment. I will have a moment due to the green thing. The moment will be like this, and the amount is just the force times the distance. The distance is a quarter chord, right? Fine. Versus what about the other way around? What about the other way around? So here is the quarter chord. The green already acts at the quarter chord, so I need to transfer the blue. When I transfer the blue, I transfer it by a force and moment. The two forces will add to each other, resulting in the resultant total lift coefficient. But then I will have a moment coming from the blue. The moment is a pitching down, and the amount is the force times the distance, right? So in either case, I will get the resultant lift force for sure. In one case, I will get a moment that varies linearly with the angle of attack. In the other scenario, I get a constant moment that is independent of the angle of attack. So obviously, this is a better candidate. The point itself is fixed, is always the quarter chord. The moment I get, because I transfer the loads to this point, is constant, independent of the angle of attack. So it seems a reasonable choice. and it has a name, and you guys may recall the name, right? Anybody remembers? Anybody remembers the name?
Aerodynamic center.
Exactly. This is the aerodynamic center. As you see, the definition of the aerodynamic center is the point at which what? The point at which any
Where the moment is constant.
exact, very good. I like this. So the moment is constant, is independent of the angle of attack, independent of alpha. So the DCM, if I differentiate DCM by alpha, CM is the moment coefficient. This should be 0 because I don't know, but there is some always I find this confusion. Some people say, well, the aerodynamic center is the point at which the moment coefficient vanishes. Well, the moment coefficient doesn't vanish. The moment coefficient vanishes at the center of pressure. But the center of pressure itself is actually not a constant point. It's not a fixed point. The aerodynamic center is the point at which the moment is independent of the angle of attack. It's a constant moment. Okay, so summary. Summary of 2D aerodynamics. Give me an airfoil. There is speed. Well, I always have some very good point called the aerodynamic center. Now on, I would never use the center of pressure again. It's always the aerodynamic center because what we have discussed already. At the aerodynamic center, what kind of loads do I have? Well, I have always the lift force, I have the drag force, and in addition, I do have what?
A moment.
A moment, exactly, because of what we just discussed. The moment, we always put it as a pitching up, although we know that it's gonna be really pitching down, and this is why the moment, what you see in the tables is always negative. So this is moment at the aerodynamic center, because I have to specify moment about what point, right? And this lift is simply 1/2 rho v squared chord times CL, and my CL is simply a constant times alpha. I'm sorry, plus a constant times alpha. This slope is close to 2 pi. Drag is 1/2 rho v squared chord times CD. CD is simply a constant tabulated for every airfoil. What about the moment at the aerodynamic center? It's 1/2 rho v squared chord, another chord, right? Because it's a moment. So if this is needed to normalize a force, I need one more length to normalize a moment. So the reference length is the chord. And there is a moment coefficient at the aerodynamic center. And this moment coefficient at the aerodynamic center is what? Is what?
A constant.
Constant, exactly. And it's typically a negative constant, as we have seen, because it's pitching down, as you see from this picture. It's exactly equal to CL naught C over 4, but you know, it doesn't matter. We just say it's a constant, and again, it's tabulated for every airfoil. So these are the 3 like tables for every airfoil shape. It gives us how CL varies with alpha linearly. The constant CD over the small angle of attack, it becomes significantly larger at larger angle of attack. We don't care about that for our civil flights. And the constant moment coefficient. Okay, so this block here is really what you need for this course. You don't need more than that for 2D aerodynamics. Actually, this is even more than enough. Any questions about this block?
Yeah, you said that usually the moment is usually a negative constant, right?
Yes.
So in the above diagram, it shows positive. Could you explain how it's usually negative?
Sure. Let's first like specify what is positive and what is negative. What is the sign convention? The sign convention for pitching moment is pitching up is positive, pitching down is negative. So where's my airplane? So here, for this airplane, pitching up is positive, pitching down is negative. All right. So when you come here, this blue moment, this is the case that we're considering, right? So this blue moment is pitching down actually. So this is why it will, whatever value you have here, it will be, You will put negative in front of it. It's not you who will put the negative, but you will find it naturally negative in the table. Like they put negative
Oh,
or
okay.
just the sign convention. Yeah.
Thank you.
You're welcome. And just reminding you that this is the angle of attack. Okay, let's go to 3D wings. And all right, yeah, we're not doing bad on time. So maybe blue, 3D wings. So I'm sorry that I will spend like few minutes with geometry, some boring stuff on geometry, but I have to discuss it anyway. How do we define the geometry of the wing? It's not just a chord now. It's the geometry is a bit more involved. Why? Because so the wing can take any shape. For example, let's say so assume that this is a wing. So like I said before, here, any section here is a two-dimensional airfoil. The wing is flying forward like this. This is V, okay? So if you can see here, this is the span, along the span of the wing. This is the y-axis. So actually the chord here, C, right? The chord length of the section at a station Y is actually a function of Y, right? It depends on Y. This whole width of the thing from tip to tip, we call it B, span of the wing. Okay, we gave it, we denoted by B. So how do we define the geometry? Well, if I want to get the area, S is the area. This is simply, let's multiply the chord by the span if it's a constant. If it's not a constant, we just integrate. So simply I integrate this C of Y times dy, and I integrate between, you know, negative b over 2 to b over 2, or I multiply by 2, and it's from 0 to b over 2. This is the area. And based on the area, I can also define something very important parameter called the aspect ratio. Like if it's a rectangular wing, it will be b over c, but for a like an unconventional wing like this, in general, this is b squared over s, b squared over area. This is standard definition for aspect ratio, and actually we give it, we denoted by AR together. And there is also the taper ratio. We denoted by lambda. This is C tip over C root, where this is C tip, the chord of the tip simply, and the chord of the root. Okay. It's typically less than 1, as you can expect. So this is for a generic wing. One last thing for any generic wing is we need a reference length. Like here, when we, what is a reference speed? Of course, it's V. So 1/2 rho V squared is a reference dynamic pressure. What was a reference length here for two-dimensional airfoil? Well, I have only one length actually, which is the chord. So I used it. So here, what is a reference length? Well, it's the chord, but the chord varies. So we need a good, should we take the root? Should we take the tip? So the community suggests the following. It's called the mean aerodynamic chord. Mean aerodynamic chord. We denote it by C bar. it has, here is the definition, it's 2 over s 0 b over 2 c squared dy. And it has the following meaning. So let's say that c bar, let's say that this is, let's say c bar is 1 meter. So you bring, how can I do that? You bring, yeah, let's do this. So this is, say, is 1 meter. And you take it like this, okay? You take the ruler 1 meter and try to move along your wing. Okay, and you find the station along the wing where this will fit as a chord, as a local chord, maybe here, right? Yes. Now, you can extend this and form your rectangular chord out of it that spans the whole thing, all right? This rectangular green chord is expected to have the same aerodynamic characteristics as your funky wing. This rectangular green wing, it's a rectangular meaning one, it's just a rectangle, so it has a constant chord throughout. So this rectangular wing, whose chord is the mean aerodynamic chord, should have the same aerodynamic characteristics as your generic wing. All right? Questions about that? So let's specify this geometry for let's make it specific to trapezoidal wings. These are the common ones.
Hey, I have a quick question.
Sure.
How did you find that length? Can you scroll up a little bit?
From this computation. So I perform this computation, I get a length, so I put it on my ruler and I try to go along my wing to match it. So
Okay, and that's in the y-axis, right?
Exactly. Yeah.
Okay, thank you.
You're welcome. For trapezoidal wings, like this question will, like the answer will be more straightforward, as we're gonna see in a minute. So let's see. Which is okay. So this is the wing axis. Okay. Okay, assume that this is a wing. So this is my, again, the wing is flying like this with the velocity v. Still, this is my y-axis. Everything is the same, as follows the definition. This is just a special case, one type of wings, where the variation of the chord with y goes linearly, right? It's just a line. So here, really, my c of y is linear in y is c root 1 plus lambda minus 1 y over b over 2. So if I have this variation for the chord as a function of y, and I plug it here to get the area, to get the c bar and all these kind of things, here are the results. It's straightforward. Alternatively, this is the area of a trapezoid, so it's not that difficult. So b c root 1 plus lambda over 2, this is the area. Still the same definition for the aspect ratio, of course, the table ratio. The c bar, let's substitute c of y here and carry out the integral. Here is the c bar over c root, it's 2 over 3, 1 plus lambda squared over 1 plus lambda. So just ready formulas, so that I don't need to carry out the integration every time I have a problem, because most of our problems will be with trapezoidal wings. They are so common. So what else? In fact, we another thing. Where is the c bar, right? Well, again, I'm gonna compute c bar from this relation, And I'm gonna have, here is my C bar. Let's try to make it vertical. Here is my C bar, and I will take it, I'll take this and try to find where is my wing station where this will fit. I actually want to increase a little bit. So let's say here is your C bar. This is my C bar. I'm gonna draw a rectangular wing that spans fully this thing. Okay, so this green wing is should have the same aerodynamic characteristics as my wing. The point here is that I have a formula, I have a relation for this distance. What's this distance? Well, this point is clear. This is the wing apex. It's clear. All right. It's the leading edge of the root chord. It's so clear. What we call wing apex. And from the wing apex, I move forward along the center line, a distance called the X bar, to arrive at this point, which is the beginning of my C bar. All right. So, and I have a relation for this X bar. What is this X bar? It's again in terms of C root. It's, I don't know, 1 plus 2 lambda over 12, aspect ratio 10, sweep leading edge. So what is this funky thing? I call it lambda. And actually this leads us to, if I want to define a wing plan form, if I want to define a wing, what variables really define a wing? There are 3 variables for a trapezoidal wing at least: aspect ratio, taper ratio, and sweep. This is the sweep angle. What do you mean by the sweep angle? Well, simply it's this angle. Okay. But as you can see, the sweep angle really depends on the line. Like this is the leading edge line. It has its own sweep angle. The trailing edge line has another sweep angle. So each station has a sweep angle. In this relation, this gamma is gamma leading edge. So it's that gamma actually, or lambda. Some people call it gamma, some people call it lambda. It's large lambda anyway. And they are all related to each other from the geometry. So as actually aspect ratio 10, the tangent of the sweep at the leading edge is aspect ratio 10, the sweep at any station n plus 4n 1 minus lambda 1 plus lambda. What do you mean 4n? So n is 0 at the leading edge, n is 1 at the trailing edge. If I want to construct a quarter chord line, then n will be a quarter, and so on. So you can get lambda of each of any line from lambda of the leading edge and vice versa. Anyway, this boring geometrical details, you can review it on your own. They will be in some appendix on the lecture, and we can discuss it whenever you want with me or with the TAs. There is no physical concepts going on. It's just a terminology by the community so that we can communicate better. That's it. Any questions?
Yeah, what are CT and CR?
That's a good question. CT is the tip chord, CR is the root chord. All right. Questions?
So they're all length, right?
Yeah, they are all length, exactly. Because remember, any section on that wing, any section like this red section, what is this red section? What does it represent really? It's a 2-dimensional airfoil. Any section is a 2-dimensional airfoil. So it has its own chord length, right? Like this one. This is a 2-dimensional airfoil. It has its own chord length, C. Now I have a section at the tip. So its length or chord length is C tip. And I have another section at the root. Its length may be larger, typically is larger. So its length is C root. what is in the fraction in the x bar zero definition? What symbol? Yeah, I think I answer this question or no? So what is in the fraction here? It's 1 plus 2 lambda over 12 aspect ratio 10 sweep, I guess. Omega, do you guys want to call it omega? All right, anyway, I mean, this funky letter is the sweep angle. AR is aspect ratio. Here is aspect ratio is B squared over S. In general, if it's a rectangular wing, so it's simply the width divided by the length, B over C. But this is the general definition, B squared over S. So the span squared over area.
And in that equation next to it, is that 4n at the end?
Yes,
of it?
yes, it's 4n. Yeah, 4n,
Okay.
1 minus lambda, rho plus lambda. And the equations will all be here. So this is, I'm going to post this online. I assume you still see my screen. I always do this. So for today, it wouldn't matter much because you have all the details. I'm going to post this, of course. But in general, I post like really a summary. You can see here, it's 1.5 pages. So this is just like what is the summary of the thing? Flight dynamics, aerodynamics, plus dynamics. Here are the types of studies and blah blah. And of course, I'm included in the summary are the equations, like because maybe when I'm writing equation online like this on the fly, I miss a half or a minus sign. So here is you make sure. So this is the equation here that you are discussing. Aspect ratio 10. I think this is lambda. Anyway, lambda leading edge is aspect ratio 10, lambda at any station n plus 4n, 1 minus lambda or 1 plus lambda. And I'm gonna attach an appendix from Etkin that has all these geometry. It's a little bit boring geometry, like I said. So let me, I still have like 7 minutes. Let me jump to the physics here.
Sorry, Professor, real quick.
Yeah,
X
sure.
bar is the location of aerodynamic center along the root chord, correct?
That's a very good question. X bar, right? You're talking about X bar, right?
Yes.
Yeah, X bar is the location of the beginning of, this is the beginning of my rectangular wing, of my mean aerodynamic chord. So now, where is the aerodynamic center? Actually, this is a good question. I'm going to discuss it in a minute. Where is the aerodynamic center? The aerodynamic center is typically at quarter chord. Well, but I have many chords. Which chord? Well, it's the mean aerodynamic chord. So really, it's at the quarter here. This is the aerodynamic center, where this distance is what? Is C bar over 4. So this point that you get is just where your C bar will start, right? So X bar is the distance from the wing apex to the point at which your C bar starts. C bar starts from here and takes the length of this C bar thing. Aerodynamic center is at the quarter of this thing, all right?
I have a question regarding that also.
Sure.
Does that mean if the two wings share the same aerodynamic properties, do they both share the same aerodynamic center?
Yes, exactly. Yeah, that's a good question.
So that means for like the overline, you have the aerodynamic center of the black wing
Exactly.
may not necessarily be at the quarter chord.
Exactly. That's a very good question. Exactly. So why this aerodynamic center, the red thing, this is really the aerodynamic center of the black wing. So it will not be at the quarter chord of the root or the tip. It's at the quarter chord of one magic station here somewhere. All right. Okay.
Okay, thank you.
You're welcome.
Is lambda a variable or is a constant?
It's a constant for each line. So this line, do you see this line? This is what we call the leading edge line. Okay, like the beginning of the wing. This is what we call the leading edge line. So it's a constant for it because it's an angle for the entire line. But let's look at the line at the back. This line, the trailing edge line, it has a different inclination, right? In general, so it has another length. Okay.
Also, how do we define the n? Like the 4n times.
The n is the station. So n runs from 0 at the leading edge to 1 at the trailing edge. If you want lambda of the leading edge, put n equals 0. If you want lambda at the trailing edge, put n equal 1. If you want lambda of anything in between, put its proportion. If I want lambda of the quarter chord line, for example, which connects all the quarter chord points, for example, well, I put n equal 1/4 here, right?
Okay.
Let me go to the meat. I'd like to finish here with the meat. This is important. So let's see. So the lift, I mean, for any three-dimensional wing, it's the same. I have lift, drag, and pitching moment at the aerodynamic center. So this is 1/2 rho v squared. Now it's the area because it's the entire wing times the CL. The drag is again 1/2 rho v squared, area times CD. The moment is 1/2 rho v squared. S, this is what was used for a force, so I need one extra length. Of course, I'm going to use the C bar because it's my reference length. This is why I invented it at the beginning. CM aerodynamic center. Fine. What is CL, CD, and CM? Well, CL is still similar. CL naught plus CL alpha times alpha. But what about CL naught? Is it still 2 pi? And what about CD? Is it still a similar number? So what happens to CL and CD when going from 2-dimensional to 3-dimensional? So what do you expect? What about lift? You guys expect lift to increase or decrease when you go from 2-dimensional to 3-dimensional? Any suggestions?
It should increase because there's infinity small segments of wing.
Yes, so exactly. So it increase. I think you're saying the other way around, right? So if it's infinity small segments, so it's better. That is for the 2-dimensional. For the 3 dimensions, finite, right? So let me say, this guy decreases and this guy increases. So actually, I lose in every aspect. So the lift decreases, the drag increases. If my wing is finite, if my wing is infinite, so it's just 2-dimensional, this is the best performance I get. But once I decide to crop it at some station, then I lose. Why is that? Let's see. I'm interested to discuss this. So here is my fuselage, which is all right. Here is my wing. The pressure on the lower side of the wing is actually higher, right, than the pressure on the top, of course. And because the result is, because of this pressure difference, I get the lift force. Fine, everything is fine. But here, near the tip, once you have a finite wing, there is a path that the air can move around the wing. And the air always moves from the lower pressure, from the higher pressure to the lower pressure. So the air will move like this. So it will create what we call the tip vortex, right? This tip vortex, oopsies, this tip vortex induces a flow field, like creates a very large downward wind or downward velocity for the air in the nearby stations. Smaller and smaller as you go away from the tip, its effect diminishes as we go in the route. Okay, what are the consequences? Let's take one station here. In this station, what does this station represent? Well, it's really an airfoil, right? Fine. Now, like I said, let's fix the airfoil and have the air coming. So this is the velocity that the wing was flying by. In addition to this velocity, now I have an induced velocity from the air, right? From the vortex, okay? So the total velocity actually is something like this, V total. So the angle of attack increased or decreased because of this?
Increase.
Actually, it's increased in negative because this is, let's think of it. So V was coming like this, right? The green. What is the angle of attack of the green? 0. What's the angle of attack of the V total now? Is actually negative. Why? Because it's coming, trying to push the wing down. It's creating negative lift. So this is a negative addition for the angle of attack. So it's as if our wing operates at a smaller angle of attack than the two-dimensional analog of it. So indeed, in the theory, we say that the angle of attack is the geometric angle of attack that you set your wing by minus the induced angle of attack. This is the induced angle of attack. And once you decrease your angle of attack, and it happens naturally out of your hand, you set your wing already on this geometric one, but what you really get is this resultant or total alpha that is less than the geometric one by the induced angle of attack. Why this happens? Because of this induced velocity. And why this happened? Because of the tip vortex. Once you decrease your angle of attack, once it decreases naturally, I mean, the lift decreases. I mean, we know that the lift varies linearly with the angle of attack. So, so at the same angle of attack, a two-dimensional wing will give you higher lift than a three-dimensional one. And the loss is coming from a famous theory. This is Prandtl lifting line theory. 1914, one of the, probably, one of the remarkable theories in the entire history of aerodynamics. I'm finishing in a couple of minutes, don't worry. So it just gives you that CL alpha is what? Let me see, do I have it here somewhere? It's probably A naught over 1 plus A naught over pi aspect ratio. A naught is simply the CL alpha of the two-dimensional wing, so it's 2 pi kind of thing, if it's not given, like I said before, CL alpha. So little l for two-dimensional, large L is for the three-dimensional. So this is, which is 2 pi. So aspect ratio infinite is a two-dimensional wing. So this is CL alpha. It goes like this. So this asymptotic value is 2 pi. And once you have it, you have any finite aspect ratio, you lose a little bit. Okay. This relation is not very accurate for, I mean, it's accurate or reasonably accurate for large aspect ratios. For small ones, there was an extended version of it. Extended lifting line theory by one of his students, one of Prandtl's students. Here is the relation. CL alpha is pi aspect ratio over 1 plus square root 1 plus kappa squared, where kappa is pi aspect ratio over A naught. No, ignore all these details. This is the relation that we will use throughout the course. All right. Just think of it like this, always in the back of your mind. Give me aspect ratio, I give you the CL alpha 3 dimension. That's it, period. Because if I have the aspect ratio, this A naught, like I said, is almost 2 pi. So I have kappa, I substitute it here, I know the aspect ratio, I get my CL alpha of the three-dimensional wing. And it's a similar behavior to this, it's just more accurate for the extended lifting line. This is what we're gonna use. So we managed to know, thanks to Prandtl, how much lift we're going to lose from 2-dimensional to 3-dimensional. What about drag? And why drag increases? Why drag increases? That's easy. Because here, remember, the lift is always normal to the incident wind. Before it was horizontal. Now it's tilted like this. So my lift force now is actually in this direction. This is the L total. And the L total has two components. One along the left, it's smaller, like we said, and one along the drag. So not only I'm operating at a smaller angle of attack, so I'm getting less lift, but also this lift is tilted a little bit so that it has a component along the drag direction. This component, what you call the induced drag. And unfortunately, it's large, so large, it's actually the same order of magnitude as the skim friction drag. So you simply doubled your drag, and it's unavoidable, it's inevitable. Why we are always obsessed about induced drag? Because it's drag due to lift, and the lift is inevitably needed, so the induced drag is unavoidable. So you're unavoidably doubling your drag force. This is why it's a big thing, and we're always obsessed in wing design with minimum induced drag. So my CD is simply CD naught plus CL squared over pi aspect ratio. This is the induced drag that is coming from Prandtl lifting line theory. And finally, the moment coefficient is very similar. It's still constant at the aerodynamic center. And we said, we already discussed that the aerodynamic center is at quarter of the mean aerodynamic chord. So this is the summary. Simply give me any three-dimensional wing. Here is the lift, here is the drag, here is the pitching moment. Next time we will do aerodynamics of the entire airplane. Sorry that I took longer time. We'll see you next time. It's in 2 days. Any questions or suggestions?
Quick question. Is that an R or a K? The in the square root.
It's kappa. You can call it K. Yeah, it's funky K. Yes. Sorry.
Funky K, got it.
Yeah. Examples? No, I mean we will, like in any homework, we will not need to solve problems on this particular thing. This is just a review of what you already should have seen before in 136. If not, that's fine. We will see next time how we can use these to construct the aerodynamics of the entire airplane. So just for the moment, I mean, it's just for the moment, we're trying to learn or to refresh our minds about these concepts of, okay, we have lift, drag, pitching moment. All this is all what I need you to know is just to be familiar with these concepts. It's not, I don't want you to be expert on using these relations. This is not the goal here. Any other questions? All right, guys, I'll post all these notes and the lecture recording. I'll see you in a couple of days. Thank you. Thank you, David.